Good evening and welcome to this Science at Melbourne event, our third for 2023. My name is Professor Moira O'Brien and I have the privilege of being the Dean of Science here at the University of Melbourne. I'll begin by acknowledging the traditional owners of the lands we are on. They are the Wurundjeri people. I also acknowledge the traditional owners and First Nations people of the lands from which our online audience is joining us from around Australia and indeed overseas. Aboriginal and Torres Strait Islander people are Australia's first scientists with deep and enduring knowledge of the land and the waters and the skies. I pay my respects to all elders, past and present, and particularly welcome any First Nations people joining us tonight. Science at Melbourne is an annual series that shares our faculty's knowledge and love of science, engages audiences in current research and empowers the community to ask questions and take action for a better world. We hope you will join us again for our final event for this year, which will be held on the 19th of October here at the Parkville campus. Tonight's event will be recorded and the video will be available on the Faculty of Science website very soon. We will also email this information to everyone who is registered, so feel free to share it. At the conclusion of this event, I also invite everybody who's here in person to join us upstairs for refreshments in the Western Gallery. This is just one of our many free public events that will be presented this week under the umbrella of the university's Science Festival, our annual interdisciplinary celebration of National Science Week, which is proudly led by the Faculty of Science. We have masterclasses, panel discussions and hands-on activities on topics ranging from the happiness of dogs to the depth of volcanoes. The Science Festival has something for everyone, so I encourage you to sign up online to any or all of the events. They are all free. The theme for National Science Week 2023 is Innovation, Empowering Future Industries. In alignment, our Faculty Festival theme is Collaboration, Innovation, Impact. And this evening's presentation is entitled Science Gets Real, from problem to lab innovation to real world impact, and it will explore all of these themes in depth. To facilitate our discussion and our exploration, we are fortunate to have Ken Jefferd, Managing Director of Research, Innovation and Commercialisation for the University of Melbourne and the university's commercialisation company, with us tonight. Ken leads a team of knowledge and technology transfer professionals who assist our researchers to partner with business, government and non-profit organisations and translate their great ideas and discoveries into benefit for society. He graduated from Cardiff University with a first-class degree in applied chemistry and gained global experience in leadership roles within BP. He was Managing Director and then Non-Executive Director of a specialist engineering and testing business operating nationally and across Southeast Asia. Ken is currently a Non-Executive Director of BioCurate, which is an Australian venture catalyst for new drug discovery in partnership with Monash University, and Carbolec, a University of Melbourne spin-out company aiming to dramatically reduce the cost and carbon footprint of industries such as steelmaking through novel electrolysis technology. He has also recently established 2 new venture capital funds for the university's innovation ecosystem. There is the $15 million Genesis Pre-Seed Fund in partnership with Breakthrough Victoria, and Tin Alley Ventures, which is a $100 million fund run by Tanara Capital. Ken is on the board of both and the investment committee of Tin Alley Ventures. With anticipation of a very fascinating discussion, I now hand over to Ken. Thank you.
Thank you, Maura. Thank you, Maura, and welcome to everyone here and online today. So let's start with the real topic. By now, hopefully everyone has recovered from that Matilda's victory on Saturday night. I hope you have. What a thrilling match. But there's an analogue for us for that. There's an Australian team that's always had the potential to win, now succeeding on a global scale. So, I'm a soccer fan, as you might be able to tell, but maybe this evening's conversation is about how we do the same with impact. How do we get Australia's potential into the World Cup of research impact, up there in the World Cup finals alongside MIT, Stanford, Oxford, Cambridge, etc. So as Moira said, my name is Ken Jefferd, and our topic this evening is to explore together from problem to lab innovation to real world impact. And this has been a topic dear to my heart for my entire career. I'd like to start by saying, I'm just going to do a few words before I introduce the panelists. I'd like to start by saying that whilst we're talking about impact today, we can't undervalue or ever forget the importance of discovery research and its funding. It's absolutely essential that we deepen our fundamental knowledge of science so that we can make the big breakthroughs that tackle the world's big problems in the future. However, it is a growing element of the social contract for all universities here and around the world that when discoveries are made that can help people, patients, families, the environment, there's a duty actually upon us to be a bit more entrepreneurial and actively enable that to happen. Impact can happen in many forms: government policy, day-to-day practices, and also what we call commercialization, which is a shorthand for new products and services that come from research, intellectual property. There are many various pathways for commercialization, which we'll explore through the talks this evening. Open source sharing, companies paying for research through a direct contract, licensing of IP that's generated at universities into companies, or start-outs and spin-outs, and we'll reflect on all of these shortly. So we're here at Melbourne University today, and some of you might think, wow, that's a pretty old traditional sandstone university. Yeah, I'm very proud to be number 14 in the world and have a heavy research intensive activity set. But fresh winds are blowing here too. We are investing heavily in the ecosystem to create new, better, easier pathways for our IP to be commercialized and for students to innovate. There's increased recognition for academics who take this path. There are entrepreneurial programs such as our Melbourne Accelerator program and Translating Research at Melbourne. There's innovation spaces such as this in Melbourne Connect here, where industry, students and academics can get together with companies. Lots of partnerships with industry, and you might be interested to know that last year we had over $350 million of research income from research end users, we call industry, that's done here at the university, and bringing in the right expertise. So for example, in my team, there's over 80 professionals now that include business development expertise, technology transfer, venture creation, and hopefully maybe some in the audience today will be inspired to join us on that journey, either in advisory roles or join the team. Specifically on startups, Moira mentioned we have recently launched 2 venture capital funds, which we're very excited about. Genesis Pre-Seed Fund and Tinali Ventures with Tanara Capital. Similar funds have genuinely transformed the ecosystems of places like Oxford and Cambridge, and we're very much hoping that happens here too. There's some great evidence that we can do it. So older examples you might have heard of, Cochlear, came out of University of Melbourne IP. You know, there's now 500,000 people around the world that can hear better as a result of that technology, and 4,000 jobs created. Melbourne IT created the domain name industry in Australia. Two more recent ones that recently listed on the ASX worth several $100 million combined. Clarity Pharmaceuticals, clinical stage listed company in radiopharmaceutical products for cancer, and Rubicon Water, which helps better use of water in agriculture. So we can do it. And there's more exciting ones in the pipeline. We've got over 30 companies in our pipeline, one of them being Synchron, which actually is several years ahead of Elon Musk in brain-computer interface technology. Remarkable stuff. So I hope you share my enthusiasm. There's big upside if we can really, really get this right for Australia, creating new industries, creating new jobs, and solving the world's big problems. So that's the opening. We're now going to hear from 3 fantastic panelists in their areas. We'll hear, they'll each do 10 minutes each, roughly, and then we'll have 45 minutes for questions. I've got a few to kick us off with. Got a couple more spare in case we don't get questions. Then we'll take questions from online and in the audience. So we have 3 speakers, Dr. Stacey Rudd, Professor David Gardner, and Dr. Shi Tang. Our first panelist is Dr. Stacey Rudd. Stacey is a postdoctoral fellow in the School of Chemistry at the university here. Her fascination with the chemistry of metals in biology and medicine led her to complete a PhD in bioinorganic chemistry in 2018. Since then, she's continued her research into developing metal-based pharmaceuticals for cancer diagnosis and therapy. As part of her research, she's established multiple commercial research partnerships, and her collaborations with these industry partners, along with world-leading clinicians, have led to 2 of the pharmaceuticals that she has developed progressing through clinical trials. Stacey, welcome you to the stage.
Okay, thank you, Kim, for that introduction. And thank you to Moira and the organisers for inviting me to speak here today. It's always really exciting for me to be able to share my work with people. And if you keep letting me going, I'll just talk your ear off. So I'll try and stick to the 10 minutes. So Ken mentioned that I'm a bioinorganic chemist. And what that really means is that I'm particularly interested in the chemistry of metals. I think that it's just absolutely fascinating. And what I'm really interested in my research is applying this chemistry to solve problems in biology and medicine. And so today I thought I'd tell you a bit of a story about how we've been doing that with one of the things that we've been working on. I do a lot of work with cancer diagnostics and therapeutics. And so I'll be talking a little bit about that today. So one of the great things in cancer research is we actually have developed a whole range of really excellent and effective drugs in recent years. We've actually gotten fairly good at it. But one of the problems that we've found is that we're not very good at predicting which patient is going to respond to a particular therapy and who isn't. And so when we give someone a really effective drug, maybe like this one that I've put up here that I'll be talking a bit about today, we're really not sure why some people don't respond to it when we think that they should. And so over recent years, we've really learnt about how in cancer, every patient is so unique. 2 people with the same disease can have really different responses to treatments. And further to that, we found that even within one single patient, every tumor can be really unique and they all behave a little bit differently. And so if the drug that we're giving someone can't actually get into every single tumor, then it's not going to treat them effectively. And so the problem is we need to know if a drug is actually going to get into every tumor in a patient. And so we thought we might have a good idea of how we could do this. What if we can actually see where the drug goes? Kind of like how we can see bones in an X-ray. And so there's an existing technology that people use in the clinic today. It's an imaging technique, kind of like getting an MRI or an X-ray that you might be familiar with. And it's this scanner that I've shown here on the right. It's called a PET scanner, nothing to do with dogs and cats. And the way that this actually works is it's basically a giant camera. And rather than detecting light and color and giving you a photo of a beautiful landscape or your pet or whatever it is, it actually creates a photograph of a very specific type of radiation. And so we thought, well, if we can turn these cancer drugs into a radioactive version that this camera can detect, we can get a picture of where that drug is going. And so our innovation was to use a radioactive metal, and we designed a molecule that can link it to existing drugs. Okay, so I've kind of represented that molecule by a little red wavy line here. That's many years of work that I'm representing with this red wavy line. But it's really taken us a long way. And so where we are at the moment is we've actually begun, well, we're almost done actually, a clinical trial to see if we can actually get this to work and whether we can see drugs going into patients. So we're currently in the final stage of a clinical trial. It's actually happening here in Melbourne as well as in Perth as well. And even from our very first patient that we recruited in this trial, we were able to see how important this really was. Okay, so I'm going to show you a scan that we got from our patient. So this patient has lung cancer. It is fairly well developed. They are late stage. And so this is the scan that we got here. And so this is a person kind of standing with their arms up like this. And you can see I've pointed out in red that big black spot in their hip, and that's a tumor. And the fact that it's black means that it's got a lot of this radiation that we've given them in it, which means there's a lot of that drug in there. And so that means that we can probably treat that tumor with that drug, and it's going to be effective. Now, it's interesting to see that they have lung cancer, but we didn't actually see much uptake in their lung tumor. And so this was really interesting to us because it means that this is showing us the difference that we can see within these patients about how some will respond and some won't. So some of their tumors will respond to therapy, but others won't. And so we can kind of tailor what kind of drugs we're giving them based on this. And we also saw in this patient a brain tumor that they were actually having symptoms from this. And so when we saw this in the scan, we knew the drug could get there. And that's really hard to deliver drugs into the brain. Your brain is really good at keeping things out. It's for good reason. But this really gave us some hope that this patient might actually respond to this type of therapy, and we can actually see that that the drug's going to go there. Now, moving this forward out of clinical trials, we've still got about a year to go, but we are well on our way there. And we're hoping that we'll be able to create a nice marketable product and actually have some impact all across the world with this. So, of course, it's quite rare actually for a chemist to be able to take what they've made in the lab and actually get it into humans and get it to market. It's so rare, in fact, that we've created a bit of a lovely, affectionate nickname for the process of getting it from the lab into people. We've called it the Valley of Death. And it's well known in pharmaceutical research because it's really where a lot of drugs fail. And there's a ton of reasons for this. There's a lot of things that you need to be able to get from the lab into people and actually make a marketable drug. And so when I was kind of looking at this graph that I just found online and borrowed for the purposes of today, I saw on this y-axis it says resources. And I thought, you know, what actually is it that we need to get over this valley of death? And I'm not the first person to question this, but I thought I'd make my own list of things that I thought was important based on my experience. And when I put together this list, I found that it really came down to three major categories. And so that was funding, getting the timing right, and having the right people. And so I'm going to tell you a bit about some of the things that were important for my journey so far with all of this, and some of the places where it went wrong. And I think that you'll see that these kind of categories and these themes really continue through all of these things that I bring up. So I thought I should start at the beginning. You know, where did this project really start? Well, it was on my bench in my lab. That's it there. I took a photo of it last week, looking a little bit messy. But it was really here doing basic science research where everything began. And so when I first made this model, this squiggly red line, I was actually a master's student. And so I didn't know much about taking something and getting it into people and making it into a product. But luckily, I had a lot of people there to help. So namely my supervisor, who was a great mentor for me and has continued to be throughout the entire process. But not only was having a mentor and the basic science funding really important for this, it was the collaborations that I had with other labs. For example, the radioactive metal that I've been using, at the time when I started this, no one was really making this radioactive metal. It was really rare. And so there was only one place where we could get it from, and that was another lab over in Perth. And so we used to fly this radioactive metal all the way over from Perth, which was fun. And I think that that's actually one of the really important things to note about this as well, is that the innovation here happened at the right time. There weren't many people working on it yet. It was new, it was fresh. And I think that the timing really, really made a big difference here. And of course, intellectual property was a really important step. So being a naive master's student, I didn't know much about how to do this, but my supervisor was adamant that we should patent this. You know, he agreed it was a great idea. And so we did. And that became so important later on in the process when we got some companies involved to kind of help us with all of this. One of the really important things was getting the word out as well. So we actually published this work in a peer-reviewed scientific journal. And it was this journal that got the attention of a pharmaceutical company. So they came to us and said, we love your idea. We're really interested in it. We want to license it. And so that's what we did. And that was such an important step. And so it was really important that we had the IP for that. Of course, everyone has different ideas on what's important. So we had to switch gears a few times about our focus, be a little bit flexible, work with this pharmaceutical company for what we both thought was important. And that connection with industry was so important for us in taking it further. Now, of course, not everything was smooth sailing. It was a very bumpy road, I won't lie. And I really came across a few things that I thought would be helpful tips for anyone who might be going through this process in the future. And so, of course, one of those is be ready to defend your work. Not everyone will think that what you've done is a good idea. Believe in yourself, trust your data. You know it's good, but you're probably going to have to convince some people. There's also going to be some competition. If you've got a good idea on how to solve a problem, chances are other people have too. One of the most important things is uncovering the unknown unknowns. So if you haven't heard this expression before, it's basically talking about all the things that there's no way you could predict were going to happen. So, for example, maybe a global pandemic is going to happen right as you're about to start your clinical trial. Or maybe you're importing a brand new radioactive metal into the country for the first time, and customs is going to have a lot of questions for you. But the most important thing that I found was don't underestimate scaling up. And so for this clinical trial, we had to make thousands of vials of this radioactive drug. And finding someone to do that was hard. And in the end, in the interest of time, thanks to the pandemic, it was me. So I actually made all of these. I couldn't resist putting up a photo because I'm quite proud. It was a lot of work. But certainly I would suggest that you think about that very early on. Hopefully you won't have a pandemic make it a little bit harder for you. And of course, the last little thing, a little bit of luck never goes astray. I certainly had a lot. In our lab, we always agree that if you draw a smiley face on your chemical reaction, it's bound to go. So I suggest that everyone does that for their most important things. So that's it for me today. Thank you so much for listening.
That's wonderful, Stacey. Thank you so much. I think people are going to be drawing smiley faces on a lot of things, not just their chemical. It guaranteed to work. Okay, you heard it here first. Thank you, Stacey. Our next speaker is Professor David Gardner, AM. David is the Group Director of ART, Scientific Innovation and Research of Virus Health. Professor Gardner is the Scientific Director of Melbourne IVF and a distinguished professor in the School of Biosciences here at the university. He is a fellow of the Australian Academy of Science and a recipient of the Distinguished Research Award from the American Society of Reproductive Medicine. In 2022, he was awarded the Order of Australia for his significant contributions to reproductive medicine. He has published more than 310 papers and chapters and has edited 16 books on IVF and embryology, making him one of the most highly cited scientists in reproductive medicine and biology in the world today. David's work on human embryo culture conditions and blastocyst transfer revolutionized how human IVF is performed. Further, his Gardner grading system for the human embryo is used worldwide as the standard selection system in human IVF. So it's a great pleasure, an honor to introduce and invite David up to talk to us.
Thank you, Ken, for those kind words. And thank you to Moira for the kind invitation and to all the faculty team for putting this amazing evening together. And welcome, everybody. I will begin. So I'm going to talk about improving human IVF. And in order to put this into context, one has to be aware of the global decline in human fertility worldwide. It really is a problem. And that has both a huge personal cost to couples who realize that they can't have children, but it also has a growing societal cost, because for the first time we can recall, developed countries all around the world, their population growth rate is below that of what we call the replacement rate. And that means that for a country to just keep at the population it is, all couples have to have 2.1 children. And most countries are well below that. And in Europe, Italy, for example, is about 1.2, and it's going down and down and down. And the problem with that, of course, is not only from a medical perspective, but that's going to have huge societal impacts as the world's getting older and there's fewer people in the workforce to take care of the aging population. So something to think about. This is the age-related decline in human fertility. I like to show this actually to all my undergraduate students because it gives them a bit of a wake-up call, because everyone thinks that it's going to last forever. Fertility goes on forever, but actually fertility in the human female starts to decline around the late 20s. And the reality is 50 years ago, in our parents' generation, people were having kids in their early 20s. And today they're having kids in their late 20s and early 30s. So they're pushing that back. And of course, with the increasing amount of professional people in the workplace, women are deferring having childbirth to later and later, only to find that, of course, now they're faced with this rather disturbing statistic that it's very, very hard for them to conceive. So that's just the age-related effect. You may want to know why, as women get older, do their eggs go bad? And that's another discussion, but it's part of the whole aging gamut that I'll come back to. Spoiler alert, oxygen has got something to do with it. Now, this is rather alarming. There's a global decline, a very rapid decline in sperm counts. These were data that were published initially in a 2017 paper on the developed countries and republished and expanded more recently in this journal here called Human Reproduction Update, where the whole world was analyzed. And you can see in 1973, average sperm counts of 101. 2018, the average sperm counts have dropped by 50%. What is going on? And it's not as if the sperm counts are dropping, it's actually the sperm quality is significantly worse too. So ladies and gentlemen, we have a global problem with reproductive health. The incidence of fertility or infertility is striking. 1 in 6 couples, 1 in 6. So every time I give a talk and I mention this statistic, I do the maths, look around the room and go, okay, 1 in 6 couples will require some form of medical intervention to achieve a pregnancy, to have a child. Currently in Australia, 5% of all children born come from test tube baby technology, 5%, 1 in 20. So when I stand there and give lectures to the biomed students, and there's 500 of them, they come down afterwards and introduce themselves. And it's really remarkable. It makes it real. And I just had the great pleasure last Friday of being in the academic procession of the graduation where my very first test tube baby PhD student graduated. So that was a big day for me, I can tell you. It was really something. To date, over 10 million test tube babies have been born. That number is growing rapidly around the world. As the problems with infertility rise, so does the number of treatments sought for this kind of thing. The problem we're faced with is that the human embryo, this is the first week of life, and it takes place in the oviduct in the uterus in the human female. There's a lot of things that are happening, but all I want to tell you is that this is a protected environment. Mum knows best. She provides the nutrients, she provides a safe environment, the right temperature, she sends signals to the offspring actually replies, and there's a dialogue going on. Now, when we try to do this in a laboratory, sadly, what we do is we grow our embryos in incubators, and more recently in these lovely blue machines, which are called time-lapse incubators with a built-in camera. But in essence, what we do is we grow embryos in a little plastic dish for up to 5 or 6 days. So this is what it looks like down the microscope. We take our culture medium and we put it in a dish, and that provides the medium, the nutrients, to support fertilization and embryo development. And the embryo grows somewhat. So that's the state of play today. And I need to talk to, but before I go on, what I need to tell you is that although we have 10 million children born, the success rates of IVF are remarkably low even to this day, although they're better than they were. Only about 1/3 of couples, 1/3, attending an infertility clinic will actually go home with a baby. So put it the other way around, 2/3 of people go home childless. And that is devastating to them, their families. The knock-on effects are enormous. So now I want to introduce you to oxidative damage, oxygen damage. I always find it quite ironic that the very gas that gives us life, the one that we're all breathing to keep us going, is the very one that kills us in the end. Most of us demise through accumulated oxidative damage, because when we use oxygen to burn our fuels in our cells, we create what we call oxygen radicals, or oxidative stress. And that has a terrible effect on our longevity, and it has a terrible effect on the egg, which has to sit there for up to 40 years. So a cell that sits in the body and is not replaced, such as the egg, is incredibly sensitive to oxidative damage. Now, in the laboratory, if we have oxidative damage, we get poor quality, low viability. We know we can measure all these kind of horrible things happening to cells, but we've seen that reduced reproductive ability of our eggs and has a profound effect on sperm motility and their DNA integrity. So there's lots of reasons why we want to research into oxidative damage. And it's a really good reason why you should all eat a balanced diet, rich in greens and healthy antioxidants. I could not stress that more. You hear it preached all the time. Trust me, as someone who's researched into antioxidants, which I'm about to show you, you can't help but do an experiment and go home and go, wait a minute, that was an amazing data set we created on sperm or embryos or even on stem cells. Why aren't we taking this? And there's something into that. And it turns out when you research into aging, oxidative damage is one of the primary causes. So please consider a very healthy balanced diet and the occasional antioxidant supplement. So when we turn to culture media, the concept of adding antioxidants has been around, as you can see down here, since 1991. And people have tended to pick one at random, and there are many antioxidants, many antioxidants, and say, well, let's add one and see what happens. And mostly they do have a positive response. They do improve development and competence. But they've been added individually. And that's not how biology works. Biology works as a functional group. So what we wanted to know is what happens if you could consider adding antioxidants in a functional group. Now, I won't bore you with the chemistry, but this is what was challenging to us. Now, here's the catch-22. I've worked in human infertility for 40 years. And the medical research councils around the world do not consider infertility a challenge. If you look at the pie that makes up medical research funding, it goes 30% to cancer, 30% to neurological disorders, and 30% to heart disease, which leaves 1% to go everywhere else. And inside that 1% is women's health and men's health. So it's very hard to get funding. So that's the backstory to what I'm about to tell you. Furthermore, because the perception is that, oh, well, a third of the patients do get pregnant in IVF, it's pretty much a done deal. We don't need to improve it. No, we do need to improve it because 2/3 of people are suffering. So we could not get any takers from grants to think that this combination, for which we had lots of good reasons for picking, would be a winning combination. So we did something different. We went straight to industry and said, we've got a great idea and we'd like you to support it. So we initiated a research contract. So it's fundamentally a very different thing, but it's almost going straight to the punchline of the joke. You grab the research, you grab a great idea, you don't sell it as research, you sell it as a solution. You never mention research to companies. You say, we've got a great solution for your problems. We have a fantastic solution for your problems. And we believe it's this. And so we targeted a company called Vitrolife. It's a biotech company in Gothenburg, Sweden, who specialize in making human embryo culture media and things like that in the IVF lab. So we negotiated a contract with them to do this work at the University of Melbourne. And it took us quite a long time, but we got there. The interesting thing is when you have, basic science, 1 minute to tell it. Okay, when you have to do basic science to cover everything you want to do, the IP is an issue because the company now owns the IP. And that could delay the publication of all your exquisite works. But actually, they were very good. They were very quickly get the IP covered and allowed us then to progress with the publication of fundamental kind of blue sky research that led to actually something tenable. And we were very proud that we were able to show that these antioxidants not only supported embryos and gametes, but they were very safe. In fact, they were much better than conditions without them, which was wonderful. We then did a pilot study with some colleagues in Japan to show that in a sibling oocyte study, older patients benefited from these antioxidants. We then did a prospective randomized trial at Melbourne IVF, where I'm the scientific director. And we've just concluded this and presented this last month in Europe. And what we found was for sperm injection into eggs, this is male factor patients, we had a higher fertilization rate, low degeneration rate. Although we saw no effect on the embryo development per se, we had more fertilized eggs per cycle, which means cumulatively pregnancy rates should go up. So we considered this a positive outcome. And as of last month, all of these media that we developed are now for sale anywhere around the world. So it's a very different approach we took, but it goes straight to the source, and it's a very rapid introduction into the target where you want. In this case, fertility clinics anywhere can now try these media. So thank you.
Thank you, David. I'm going to go home and eat some cabbage, I think, after hearing that. Wonderful, thank you. Our final panelist is Dr. Shi Tang. Shi is a research fellow at Exciton Science within the School of Chemistry here in the Faculty of Science at Melbourne University. He works on high-performance polar ionic devices based on perovskite materials. He holds a PhD in physics from the University of Sydney, where he develops solar cells for space applications in collaboration with Exciton Science, ANSTO, and CSIRO. Shi, we're looking forward to hearing your presentation.
Thanks for the introduction. Thanks, Maria and the team, to get me involved. My great honor to be here to share my experience towards the space. So as you may see, the story happens not from the ground. They are actually 300 kilometers away from here. And why are we doing this? We are not doing this because it is easy. Instead, it is because it's difficult and we need them. And we could see solar cells, they are born for space. And the very beginning, just in the 1945, the first solar cell was demonstrated. Just 4 years afterwards, people sending them all the way into the space together with the launch of NASA. And now, the International Space Station, they are totally powered by solar cells. And recently, what we have seen, there is a huge increase for the satellite, and every satellite requires a solar panel to power and to supply electricity. And what I'm working on for my PhD is called perovskite solar cell. So what is a perovskite solar cell? The perovskite solar cell is just in the structure of ABX3, like the blue color, red color, and the small atom in the middle. They arrange in the form of ABX3. And when I'm doing my PhD, I'm stacking the layers all the way from the very top sapphire to the down until I finish all the layers. So you see, the more the layers, the lower the successful rate. So I have been struggling a lot all the way through this process. But it is worthwhile because it could give me higher efficiency. Just within the 10 years, it is already approaching the target through the market, which are dominant. So before we really start where we want to send through our solar cell, we do an analysis where the solar cell will be in a short time really goes to. The first will be the moon, but that's so far away, you know. So we couldn't be sending human being all the way to moon just in 5 years. And the other market is called low Earth orbit, which is approximately 300 kilometers away from the ground. Why it is such a big market all the way there? Because the satellite, like the Starlinks, we could using the satellite within the low Earth orbit for powering the internet, and we don't need building any station on the ground, and it is quite convenient. Even though in the northern territory, we could still receive the signal, and that's quite convenient. And the last one will be Mars. Elon Musk, he's really fantastic for moving to the Mars, but still it takes some time. So let's just sitting on the ground and trying to find some market which will be benefit to everyone in the coming 10 years to say. And the advantage for perovskite, as I just mentioned, it is high power to weight ratio, which means with the same weight, we could offer in more electricity. And the next thing is the much lower cost. We don't need to have a huge furnace to grow 3-5 material. And we also don't need to spend so much protection to avoid the damage under the radiation condition in the low Earth orbit. So what we start with is we trying to know how the solar cell performance under the radiation. So here is what a normal solar cell works. When we have the light, we actually give extra energy within the solar cell. In that way, we could elevate some particle to a high energy. And afterwards, we're getting this energy into electricity. But what if we sending a solar cell to the low Earth orbit? We have one challenging. It is called proton radiation. And proton, they are the positive charge particles. They are also high energy. So now we have competition. First, the solar cell, it will give the high energy to move the particle to a high energy state. And the second thing is the high energy of proton. It may generate some defect. In this way, the defect will just trap the particles, and the particles are not contributing to the electricity. So when we consider this one, we think, oh, we need some equipment, but where we get money? And Astronaut Science actually raised me up. So I get funding from Astronaut Science. I could build equipment and the system to characterize how this physical process happens and how to quantify them. So here is the challenge, how the proton challenge the solar cell efficiency. So we found there is a kind of process called diffusion. In the layer stack, we have a kind of chemical element. It contains fluoride. And once it is in the space radiation condition, the fluoride actually diffuse all the way into the absorbed materials, which generating the defect. So how we see this kind of evidence? That's from the very top one. We see the increase, then decrease. It is a kind of evidence by tracing the element distribution with respect to the thickness of the materials. But if we change to other materials combination, we could actually avoid this kind of diffusion process. And in this way, the solar cells are supposed to be more stable in the space radiation. And now we know how the solar cell get damaged within the space. And we're trying to recover the solar cell. After a few steps, we make them still the same as what we before launch. And the thing we call is thermal vacuum. So in the space, the solar cell will be facing the sun and it will get heated to an elevated temperature. For now, for the experiment, we're setting it to 80 degrees Celsius, which will be the above average temperature. And the vacuum that's quite normal in the space, we pull the solar cell into this kind of condition. And what we found is, if we choose the materials properly, we could actually recover the solar cell 100%. That means the solar cell, what we launch, that's how much electricity we could get. And at the end of the lifetime, we could still get the same electricity if it could be heated up in the space. And this really happens in the space. And we also have some pathway. We try to commercialize this product. So first, we have the concept of demonstration within the lab. We could bend in the solar cell, even though with the tweezer, that's still very stable. And also, we have been patented for 3 of them. And the next thing is we are in cooperation with the team to send the solar cell into space. For this stage, I could do that much. For that one, only to say expecto patronum, to protect them. And the last thing is we also have a startup company called Eureka Power that will be in charge of all the commercialization for our technology and their journey to the space in the future. Thank you all. I need to have one more thing is this is not my own work. That's actually a work from our research world. Without them, I couldn't be here. Thank you.
Oh. I think we managed to jump on ahead there. That's the punchline. There we go. Wonderful. Thank you, Shi. Well, 3 fascinating presentations. I hope you agree. So now we're going to have about 40 minutes, 45 minutes, Rebecca, I think, of questions. So I've got a couple whilst we get going. We'll then switch between the audience here in the room and online. So if you're online, please do type in your questions and we'll read them out to our wonderful panelists. Okay, so I'll start. So I'd really like to think about the personal side of this. So on a really personal level, sort of your why, what inspired you to focus on applying your research to solve a real world problem as opposed to pure discovery research? I'm really interested in that. Stacey, you're sat right next to me. Why don't we start with
Lucky
you?
first, all right. I guess to that, I have to say I actually do both. So when I'm in the lab, some of what I'm doing is, I'd like to say just for fun, but let's say it's blue sky research. It's really kind of the fundamental chemistry, trying to get to understand how things work. And then I'm also trying to use that to apply it to real world problems. And I think that applying it to problems really kind of keeps it a little bit more interesting for me as well. And as well, it certainly helps me to keep motivated when things don't go well. So in the lab, certainly I would say most of what you do doesn't work. That's why it's research. And sometimes you need that little bit of a pick-me-up to kind of be like, why am I doing this? Oh, that's right, for a good reason. Yeah. And so I think that is kind of what really motivates me. Yeah.
Fantastic.
For me, definitely because I was in awe, fell in love with the embryo from day one as a honors student, when we couldn't grow embryos. But I just found the whole concept of one cell giving rise to every cell in the body, that was fantastic. And so I went on this journey of being an academic, and I did the classic training and did postdocs around the world. And I loved it. I absolutely loved doing the basic research and having that experience. But it was also aware that, IVF was in its infancy and it was very unsuccessful. So I decided really that it would be one of these areas that I could actually potentially have an impact and see really good ideas go from an experiment to actually helping somebody. And so I moved to Australia as a result of that. And I came in 1989 to work with Carl Wood and Alan Trounston at Monash back then, when they were really the world leaders of IVF. And I said, I want to do research, but I really want to have a go at translation. Could I train as a clinical embryologist and get to know what it's really like? So I did that. And the turning point, I'm sure a lot of people in my field have had the same experience, was when I went to do my first patient myself. So I've been trained. And the look of desperation in this poor woman's eyes when I actually went to do the name check, and she was pouring tears, and she just looked at me, she goes, please, please get me pregnant. And I went, oh my God, this is as far from an experiment as I've ever experienced. And it was life-changing. Yeah. And I walked into the lab and everyone could see I was moved. And they said, are you okay? I said, I think so. And I was just driven from that moment that I knew that's what I had to do. And so I love science, and I love blue sky stuff, and I'm grateful to all my graduate students, but having this capacity and this vision of actually making something tangible to help people, and millions of people, it just keeps me going. And that's why I do what I do.
That's incredibly inspirational. Thank you, David.
Yeah, for me, I think that's my astronaut is my first choice for my future work. But unfortunately, I have a scar on my hand, so I couldn't be an astronaut after like 10 years old. But when I get this opportunity to say we send solar cell into space, the ever first one in the Australia, I say I'm in. Nothing else.
Oh, that's great. That's great. Maybe you get to take one of your solar cells up one day, Shi. Yeah. You never know. Okay, one more question for me, and then we'll go online first. So I think Stacey shared a bit of it, but we'll start at the other end. So thinking about what you've done with commercialization and translating and applying the research so far, what were one of the 2 things that really worked? And also, if you had a magic wand, what 1 or 2 changes would you make to our ecosystem here to improve your ability to have a real world impact and commercialize things. And I'd like you to really go for it. It could be government, it could be the university, you've got the Dean of Science sat right here, you've got the head of commercialization sat right here, it could be your own department, it could be industry. What would you, so what's gone well, and what would you love to change to help yourself and other folks wanted to commercialize their research? Why don't we start with you, David?
Okay.
To mix it up.
I think fortuitously, as you can see, I'm not the youngest person on the stage. So I've seen a lot of changes, and I've actually seen in my time at the University of Melbourne, amazing changes in terms of this innovation drive. So, and the other thing is this whole commercialization as well is until recently was a dirty word in academia. It wasn't palatable. When I was head of school, I made this big push to drive innovation translation. I wouldn't call it commercialization because they would just kick me out of the room, but innovation translation to really make my team, most of whom were older than me, realize that we were accountable to society and that we should be looking at ways more directly that we can find solutions to problems, not present research ideas. So with that, but the challenge back then was you weren't around. And we sat around with great ideas and nowhere to go, because we knew that to commercialize them, we'd need IP protection, which, you know, can be around 10, 20,000 for your first round, but it rapidly ramps up after a year to about 100 grand. And I didn't have that, as most lab heads don't. And the university went, okay, we'll have a look. 6 months would go by, we're still looking. A year would go by, but come on, it was a great idea. Now other people are publishing around it. Yeah, we decided we're too late. It was like, oh. And so this would be time and time and time. So I think those days are gone, thank goodness. The other thing, I think it's getting people to see it as not a dirty word, commercialization, but to embrace it. And I think what would be really good is if we could actually get first week or first month of a graduate student's training was with you. But I mean that sincerely. I mean, to actually understand from day one what you can do and how to do it. Because people doing PhDs are not, you know, without a bit of brain power, right? They're smart people. And yet they're really smart like this. And then they've no idea how all of this works. If they had that insight from day one, that would be maybe a catalyst to sort of want them to do more and be more creative, and to actually see that it's not a dirty word, that it's actually a really fulfilling and a proper end to what we do. And it's very fulfilling, and it's wonderful to hear these stories, really, at such young part of their careers, to be able to get to that level. I'm in awe, really, of where they're at. So for us, it was a different process. We went and looked for people's problems, and then came up with solutions, and then went to pitch the solutions to people. And that was a good learning curve. Don't ever ask for research money. Always go and tell them, we've got a great solution for you.
Okay, I hope you noted that solution, and I'm going to clear my diary. Shi?
Yes, I think for me is the stage that incorporate the IP team and learn to listen people from the industry. Because for me, when I start this project, I'm more like from the scientific role, how I could get this thing into publishing stuff. I actually did not start considering how I actually push this one all the way into market. But I think if I got a chance to just get the IP team involved, I know what industry really want me to do. And I may have some bad ideas. Then it will not be like 3 patents. We may got 30. So I think in that way, we could plan our project even faster and get the process more smooth, I would say, because we did so many times within the research side. And then for me, I'm just a PhD student, narrow things down, improve the technical part, but I lost the chance to listen to others, what really matters, what really want. That's the thing I would say. If I got a chance, I will reverse the sequence.
Okay, fantastic, Shi.
Gosh, some really good points. And it's actually kind of making me change my answer as I'm sitting here. I think, yeah, so I guess for things that were really important and went well, I think I'm going to copy you too and say that the IP was just so important for everything that came later on. And I think I mentioned in my talk before, you know, I was a master's student when that all kind of happened. And so your point about very interesting about getting PhDs and everyone to kind of learn a bit about this is I think a really good idea actually, because I just had no idea how to go about doing that or how important it was or anything like that. I was lucky enough to have my supervisor say, we need to patent this. This is going to be really important. And I can remember actually, so you can't publicly disclose things before you have your patent. And I had my final master's presentation coming up. And I was like, can we do this quickly, please? I'm really stressed. And it was so lucky that he did say, no, we need to do this, Stacey, because it really led to everything that came afterwards. And so that was a really important step, I think. And I think you were saying as well, what if I had a magic wand, what would I change? And I think that's probably coming from the early researcher kind of perspective here, but and it's probably been mentioned at many panel discussions before. But I've personally really struggled with the ecosystem that we have in terms of research funding. So. You know, we're constantly applying for grants, and the grants will only go for maybe a couple of years, and they're so competitive that essentially, as researchers, we don't know if we've got a job in a couple of years. We don't know if we continue working on our project and we can actually be there to take it further. And so that's really challenging. I've been really lucky to be able to get some grants to keep going. But for example, the last one that the last big one that I got that I'm currently on now, that one had an 8% success rate. And that was one of the major schemes in Australia for funding medical research. And so only 8% of applications were actually successful. And I am absolutely 100% sure that there were more than 8% really amazing ideas that people had in those applications. And so I think, I don't know what the solution is here and where the more funding can come from, but I think that having a little bit more of a secure funding for longer would really make a difference for a lot of people.
No, that's yep. You're not the first person to mention that, and it is a challenging one in terms, David, of the point around very early career researchers, PhDs. We obviously speak to a lot of universities around the world that are very good at this, and that's a consistent message that comes back. PhDs, the postdocs, this is the engine room of your commercialization. So extra support there, please.
But I wouldn't stop there. I mean, the senior academics, some of whom are very set in their ways, you know, it's need to be, yes, you can teach an old dog new tricks, and they need to be aware of it. I remember I was head of what was zoology for 6 years, and I challenged them, and I had marine biologists, ecologists, and they looked at me and said, how can we be commercial? I said, don't use the term commercial. We have solutions to lots of problems. Let's go find them. Within 6 years, the Department of Zoology had the highest percentage of industry-funded grants in the entire university. And it's just, I changed their perception of what commercialization was. And there's a lot of funding out there, and people are very keen to tap in to the universities. The problem is a lot of small companies don't even know what we do. So it's kind of this gulf between the two worlds. There's the real world and academia, and it's just reaching out literally to make those connections. And that's what we did, and that's what I know you guys do. And that has a profound impact. And then I think it also puts the universities in a much more palatable light in terms of society. Because a lot of people perhaps don't get what we're trying to do. It's these ivory towers. Actually, it's far from that. We're desperate to actually translate our ideas. And if they see that more of the dollars that are invested in these young people, in your research grants, actually pays back, which it does in spades. Actually, it's a great return on investment, is research. And we could get those relationships. I think that could change the perception of what we're trying to do and who we are.
I completely agree with that, David. Thank you. So those are a couple of questions to get us going. Online. How do we get the online questions? There we are. Okay.
Oh, this way. Hi, Ken and everyone. Amazing presentation. We've had a question from online.
what are some of the best ways we can get info and keep up to date with commercialisation? We're unsure if this has come from someone at Uni Melb or not, but how to keep up to date with news?
Well, I'm looking at you, Rebecca. So well, there'd be various ways that I talk about, and at the end, I'll put up a slide if you want more direct information who to talk to. So we'll answer that question and who to talk to at the end. But I think the very best way is to be engaged with the university. So there's a very active website which is regularly updated on what's happening. There are events like this, but we really do encourage, if you're serious and interested, to build personal relationships with the key people at the university. If you don't know where to start, well, we'll get to the punchline. If you don't know where to start, we do have a business development group that you can talk to, and they will help you navigate through the whole system. Once you've built your own personal relationships, if it's in any of the areas that you've heard about today, you'll build personal relationships with the academic researchers, be they professors or with the academic teams themselves. So those would be the ways. And then there's always events like this which you can come along and be part of. And that is actually a feature that you see in the overseas ecosystems, which I'm very keen to focus on, and we're focusing on very hard shortly. Is it was described to me, who's seen the show Bridgerton? Did anyone see the show Bridgerton? Some hands up. So this is kind of a quirky thing where back in the day, the royal family, all the royals in the British society meet each other in these series of garden parties. And all these people go to this series of parties. They all sort of go to the same party, and they're all meeting each other and connecting. So I met a venture capital firm, very successful one in Cambridge, and they said, the Cambridge ecosystem is like a whole series of Bridgerton garden parties. So you get into the system, and the people you're there. So the incredible research like we got on stage are there. Fellow investors, industry are there. Government agencies are there. Incubator programs are there. Technology parks are there. And you have events with themes just like this. We'll go up and have drinks. And you'll talk to people, and you'll connect, and you'll find people. And that is how a lot of these ecosystems work in Boston, Cambridge, Oxford, Imperial, MIT, Stanford. We know this because we speak to them, and we're trying to stimulate that here. So that's another very active way. Just get into the ecosystem, meet people, make connections, build your own relationships, follow where your interest lies. But if you don't know where to start, you can contact the business development team. You can look online, and if you want to contribute to the system yourself, if you're an advisor, we've actually got someone who manages the community of people who want to be advisors, mentors to research teams. So we jump to the punchline at the end of the talk, but thank you for the question. Would anyone else like to add to that?
I think you said it all.
Yeah, I think you covered it.
Yeah, absolutely.
Great. Well, let's go to a question here. I can see a hand up at the front here.
Thanks. Hi, I'm definitely not someone who's in the scientific community. I do professional services in the infrastructure sector, so just having a look, basically. It's just an interesting one. How do you be collaborative when you're working on research together or developing an idea, as well as being commercial? Because at what point does someone's little contribution earn them a little bite of the cherry? Like, how does it? I'm just curious because I'm not sure. But also, is there something that crosses everyone's minds? You know, if we're being highly trained, for example, in the future, if young scientists are being told how to protect their IP all the way along the trail, are they going to be maybe incentivized to be a little bit less collaborative, a little bit more reserved, you know, in the way that they develop ideas? And does that have any negative consequences on research?
Wonderful questions. David,
I think
would you like to?
the second part of your question, if I may, about the collaboration. Science is not what it used to be 20, 30 years ago where we all had our labs. Now we all work in big teams across disciplines because science has just become so mind-blowingly wonderful very quickly that we realize that we can't do anything in silos. We have to work together with different things, whether they're engineers or chemists, to do that. So I actually think having the IP strategy actually creates the capacity for collaboration. It's not counterintuitive, it's actually, it fosters it. And through Ken's office and lots of other offices in universities and industry, you know, just to have these contracts, these non-disclosure contracts that you can sign, everyone then can talk freely amongst each other. It's very transparent. And I think that's really refreshing too. It's really wonderful. So I'd be keen to hear your experience in this.
For me, I mean, talking about the point about collaboration that you're asking about as well. In my personal experience, I mean, I agree with David. Science now is so collaborative. No one, well, maybe someone is, but no one that I know is really kind of just doing their own thing, working on their own project. We're all working together with so many other labs, people with different expertise, people from different fields. And that's kind of just the norm of how it is and how we all work. And so I think inherently we're all kind of used to that sort of working together as a team kind of mentality. And so when it comes to protecting our intellectual property and all of that, in my experience, it's been very much, everyone's like, oh, and you should probably be on this as well. And so should you, you did this part. And everyone, you know, we tend to work with people who, you know, we choose people that we get along with well, and we all work together well. Otherwise, we wouldn't work together at all. And so I find it's quite a healthy working relationship to have. Really, we're all kind of fostering that sort of working together environment. I think that sometimes when you do kind of get a company involved, which is I think what you were the first sort of part of your question, then sometimes I think that overarching, you tend to have the same kind of goal. I want my work to be out there and used by people. They want to create a product that is used by people. So we share that kind of goal. But sometimes the way that we want to get there might be a little bit different. Someone was mentioning before about some, you know, I think it might have been you, David, but I could be wrong, about maybe companies won't want to publish work at a certain time, and we rely so much on our publications that's something that sometimes comes up a little bit. But generally, I don't know, it's been a positive experience for me at least so far.
And I think most companies know that. I think they know the rules of engagement is they know that on this side of it we need to publish, and they respect that. So occasionally it doesn't go the way you think, but for the most part they really try to help and get those provisional patents in, so you can go to the conference and talk about it, or you can go to the beginning of that. So
For me, I think my collaboration went quite smoothly. So we had a regular meeting at the very beginning, which we sort out the student agreement, the IP belongings, and the university business department also help us out to go through the IP problem. So we just divided IP into two areas. One area is for radiation, and the other area is for solar cell. The radiation goes all the way to Anston, and the solar cell part goes to Sydney Uni. I'm the co-supervised student, so they will be share the publication, and also they will archive my PhD thesis all the way like that. So I would say just solve the hard part in the very beginning, and everything will be smooth afterwards.
Wonderful. And just to finish the question off, if there is a net commercial financial benefit, the university does share it with the founders and the university, and some of it comes back to fund teams like mine. Delhi, we're going to go online first, Delhi, if we may. I'm going to flip between the two, but I'll come back to you, Delhi.
No, we can go in the room.
Okay, you're off.
Thanks, Ken. I have two questions, one to Ken, one to David. Maybe go to David first. And when you have approached the industry direct, it's an amazing approach, and to pull out a potential solution, but you went to the international institution. In Australia, we have the culture, industry investing in R&D is not strong. Like when I go to the industry, I'm pretty successful getting industry money. But when I go to the industry partner, say to ask for money, with our current 2.5 multiplier, it's expensive. They say.
I have to agree with you. We are very expensive to work in this kind of contract. And yeah, so for those of you who don't get it, so basically, if you don't create your IP yourself and you do this contract research, the university charges like a wounded bull to get the money back. Oh, and some. And so it makes doing that project in Melbourne 4 to 5 times more than it would be, say, in America.
Yeah.
And so you've really got to be persuasive to make sure they keep coming. And it is hard. And I think that's something that needs to be addressed.
Well,
if Melbourne's going to be serious about keeping research contracts, I think what Ken, you're talking about is generating IP, and what your stories are fine. But that is a bit of an Achilles for us. And yes, but that can be addressed. That can be addressed.
Good.
My dean is not looking very approving at me, my
the entry-level postdoc fellow costs almost $500,000.
Yeah, you've got to do a trade-off. You've got to get it right, and I think you should negotiate with the companies to do that. Because I mean, I know we could lose, contracts as a result because we're just not competitive.
The same question to Ken in the echo what you asked, and I'm actually director of ARC Hub, Smart Fertilizer, but it's in agriculture, it's kind of research, require a multidisciplinary large team. The challenge is, for example, and Ken, we're developing the new nitrification inhibitor. The key inventors are the chemists, but it require the whole hub to help in the field, the agriculture field evaluation. But when we apply for, listen, a patent, based on current definition, only 2 or 3 people can be qualified. How can we recognize the rest of the whole hub when it comes to commercializing stage? So it's a challenge. I'm working with your team to how can we define some inventor, some co-contributor. So it's not simple when you develop really complex issues.
I think the question was, how do we recognize the broader team? And that's something you've got to work through on a project by project basis. The system is designed to be able to do that. The major lesson we've got is do that up front. Don't try and do that at the end, because suddenly, that's problematic. There are a lot of people will appear, so agree that up front, do the hard work up front to define who the inventors are, who the contributors are, and we're not solving this problem. We're not the first people to solve that problem, so we can solve it, but you just do need to work it through. You do need to work it through. So I'm glad you're working with the team. Thank you. I see a hand up, been up for a while back there.
Thank you. Hi, everyone. Thank you again. That was great presentations. I work broadly in science communication, and I've sort of flipped between helping scientists to communicate and helping scientists to communicate, or just becoming a better communicator, and I guess partnering with scientists to help make impact. And I guess I say that because it sounds like I'm hearing a similar thing where there's this flip between wanting to partner with business services, but also helping upskill scientists to be better with commercialization. So I guess my question is, are we putting too much pressure on scientists to be all the things? And is a better solution to be partnering with a number of different experts in different research areas? I mean, I guess my question is there too much pressure on scientists right now to be all the things, really? And is it something that's sort of compromising the impact that you make?
Who wants to take that one first? Let's ask the scientists.
I think for scientists to learn everything, I think physically it is not that possible because we are just human beings, but we definitely need help from others. Like when I start my PhD, I have really poor communication skill, and then I get a training, I getting better, but I think still I couldn't finish all the things. So in that way, we definitely like business uni within the university, like everyone helped me out. So like generating IP, that part That's what I could do. But before I submit a manuscript or publish something, I could go for university, for faculty, for school, for the help. Never afraid of asking for help. But just if you have any concern, just talk to people that will help you out. So that's also initially when I'm doing my personality test, I'm quite internal, and afterwards I could talk to people and then seeing different things. They really help a lot. So I will say communication will help a lot, and then not just limiting to yourself. Think of the whole world, the group and others, and then collaborate. That's the thing to making scientists get out.
Fantastic. I'm really glad to hear that, Shi. That's great. And they did a brilliant presentation. So.
I guess I might add to that as well. Firstly, thank you, because I really don't want to have to do all of that as well. And that's not out of a lack of interest or anything. It's just that I honestly would have no idea where to start. And I would be very inexperienced in kind of doing all of that and really taking it all the way along. But I think that what would definitely help is if we kind of had a better idea of how to start and what the process kind of looked like. If we just had a little bit more of an overview, maybe that would help. That would have helped me for sure. I really didn't know what I was in for. And I think just having that kind of overview would be really good, so that then we can even better help the commercialization team once we kind of hand things over to them. Yeah, so I think that I think that just knowing a bit more about the process would be helpful, but we don't necessarily need to be experts in it.
Yeah, and I would say you indicated, is it too much for people to take on board? I think if you did it retrospectively, it's terrifying. But I think if you did it as you came in, you know, and I think like the world has changed, everything's changed, and for the better mostly. And this would be a great example of my young colleagues getting mentorship right at the start. You don't necessarily have to do all of those things. Just knowing that that's there, I think, is less terrifying than all of a sudden you've got an idea and someone says, "Oh, have you got IP?" And you go, "Why, what?" You know, I mean, seriously, I mean, and so they're really less intimidated by it. It just becomes the norm, the conversation. And I think it should.
Yeah. And I would say, statistically, those academics that do really well in translation typically are also great with publishing in raw academics. So, case point here, the 310 papers, David. Yeah. That's typical. That's actually very typical. Often because you're partnering with industry, other people, you're understanding problems, you've got more collaboration, papers that are cited with industry partners tend to get cited more. So it feeds on itself. So it's not the Venn diagram overlaps. It's also not very typical if you go down the startup path or spin-out path. It's very atypical for the researcher to leave and be the CEO, the lead researcher. Extremely unusual. And we don't, to be honest, we're not setting up to support that. We're setting up to help bring the right expertise around our colleagues. So that they've got the expertise, but I think Stacey's point is amazing, that you've got to have an overview of what's coming, so you know what's coming early on in your career, so you're ready for it. So, and the other thing that gives me hope is that, like I said, other ecosystems around the world have cracked this code, and very successfully. So, you know, Garden Party is part of it, but also the expertise and the support, and we are getting there. You know, things like Denali Ventures, you know, now exists. First one in Australia that Melbourne's pioneered. That transformed Oxford. You go back 10 years ago, and it's a very different place. So we are putting in the blocks in, and I hope my colleagues don't feel too much pressure to do that, because we're trying to bring the support as well alongside it.
I don't feel pressure. I actually feel relieved that you're there for the first time. It's amazing to be here on this stage, engaging with you and these wonderful people. I just feel very positive about the future, actually.
So do I.
Yeah.
So do I. Right, questions. Now we're coming. We'll start here, and then we'll come to you in the middle, sir.
Thanks for your presentations, really interesting. So I'm from IP Australia, the government agency that administers IP rights. So really great to hear that you all got IP and was successful. So I'm interested to hear if you had to overcome any barriers in the journey to get that IP.
I guess I would say yes. My naivety was the first, for sure. I mean, you made a joke before about, oh, have you got IP on that? And someone saying, what's that? And that was me. That was actually
That
me.
was
And I had no idea what was involved. I'd heard of a patent before, and I thought, oh, what does that actually mean? What can you patent? What can't you patent? What constitutes, an original kind of invention? And I'm still not sure I really know. I think I have a better idea, but it's been a real learning curve there, and also patents cost a lot of money. So that was a new thing to learn as well. I kind of assumed you didn't have to pay for it, but you do. And so you need to find someone who's willing to cover those costs, whether that be the university supporting you with that, or be that someone in industry who thinks you've got a great idea. And so that was also a bit of a challenge as well.
For me, I think the challenge comes from the communication to the non-expert. When the IP is actually being reviewed, it is more like a broad people, not just the expert within the same field. So you couldn't expect they understand the concept just go through the figures. So the way is how to making my research result to be understandable by the general public, and then I could get the novelty understand by the examiner. That's the way, but university really help us out. We submit the IP disclosure and the university review and have piles of questions. I would say like, still now I'm afraid of seeing the long list of the question, but this question actually helped me out to explain the ideas to the patent attorney, and then they draft the application for us actually, and then we get it through. So I will say that's how to conceive this idea to the general public.
Yeah.
Anything to add, David?
Well, I would say that, again, things have changed dramatically. 15 years ago, it was very difficult to get support for IP at a university. They didn't have this kind of initiatives that you're heading up. So I don't want to dwell on that. I want to reimagine that I'm young again and could come into your office and say, my God, I've got all these ideas now. And I've got an insight. Of course, hindsight is 2020, but now we're going to have all these courses teaching all these wonderful people as they start on the pathways that we should be putting together. So yeah, it's really important, but I think, the whole concept is awareness of IP, the significance of what it is, and that really, those dinner parties or garden parties aren't going to happen without it, because the guests aren't going to come unless you're holding that IP ticket. Then they'll talk to you.
Yeah. And it is. So one of the big problems, David, we discovered a couple of years back is just the speed of it. So, the tech transfer team now, they've got their thing, and they've got it at 222. In 2 days, they're going to respond to you. 2 weeks, they're going to have an initial conversation. And in 2 months, they're going to give you a view of, is there novelty? Is this something? And then it might take longer, depending on the long list of questions, but you need to go through those. And then there's other ways to increase. So in our tech transfer team, knowledge transfer team, there's internships. So if there's any PhDs or postdocs online or in the room, you can do an internship in my team a day a week, 6 months. You get a whole bunch of training. You can help us out with tech assessments. You can learn how to do it. You're not left flying blind. Don't worry, someone will check it. But it's a great way to learn it. It helps us out enormously to get through tech assessments a lot quicker, because speed is very important, very, very important for everybody. Recognize that. And there's also some training and development for those that do it. So I'd encourage you to think about that if you're online or in the room and that's of interest. Thank you.
Thank you very much. It's really great to see that there's some real positivity about going forward with commercialisation or solution solving, because we've had a history in Australia of sort of talking about it and having great research, but really, to be frank, not really succeeding in the commercialisation end. So fantastic to have this conversation and opportunity. I'd like to just.
Sounds like it's gone off.
Oh, thanks. That's the wrong way. I'd like to just look at the broad picture a little bit. There's in research we can sort of be focused on solving a relatively narrow problem, and in fact, even just going to what you were talking about, David. The elephant in the room is the age of the people involved, and your graph made that perfectly clear. So when you talk about 1 in 3 succeeding, the age of the people you're talking about just completely changes everything. So so in that case, my question is, what do you do about actually addressing the broad problem rather than the narrow technical problem? And for the pharmaceuticals, it might be, what do we do to try and reduce the incidence of the disease rather than just solving the problem, assuming that we're going to go down this terrible path where everyone's got bad lifestyles and exposed to lots of chemicals and so on. So is there a way that we can broaden the picture and not just solve the narrow technical problem?
Yes, it's called, I don't mean to be facetious, but I would call it education and blue sky research and fundamental research. Those are the two things. To get to the basics of the etiology of the problems, prevention is better than cure every time, right? So we're talking about, well, you're okay, you're making some sense, but we're talking about, diseases. And if we can get to the etiology of the disease, that's so much better. But in order to have that, you still need better education. So I'm always heartbroken when people still, and I think we've been screaming from the rooftops for forever that, reproductive lifespan is very short. And I'm always shocked when a patient comes in and is devastated that she's 39 and is having problems. And I'm thinking, but yeah, okay, we've failed somehow in communication. Or as you were alluding to, there's problems in the environment. We've got some of the best environmental toxicologists and developmental biologists in this university, to fund them to do those kind of things that we could actually then make recommendations to the academy, to the government, about what we really should be doing holistically. So head off the trouble before it gets there. Exactly. So I think those are the things and that's the role of the university. I mean, we're talking about a new facet of the university, but what you're addressing, in my mind, is the fundamental core of university business: education and research, fundamental research to crack the problem. Yeah. So we need more funding. The government just needs to give us the money, not you. The government needs to give you the money, and
I'd also add to that this sense of interdisciplinarity. So in this university, we have some of the wonderful minds in the social sciences, and I think that's something I've seen increasing awareness and interdisciplinary institute to solve the whole problem. Working together with colleagues from other disciplines. I don't know if you see it, but I'm seeing that a lot more. Yeah. So you can attack the broad as well as the narrow, but it's the magic mix, right? There's no one perfect solution. I think we should be attacking these problems from multiple dimensions.
I think I might add as well that I think that sometimes even attacking these narrow problems really informs us about the big picture as well. So just to use my presentation and my work as an example, that was kind of looking at one particular drug and how that works in people. But one of the other things that's going to come from my research is that drug actually, the way that it works is it stimulates your immune system to then attack your cancer for you. And we don't understand all of the underlying processes that go along with that. And so even by being able to see what's going on in each individual patient, we're going to get more and more information about how the immune system actually works in cancer biology. And so all of these little pieces of these narrow questions that we're looking at really form the big picture as well, and kind of teach us a little bit along the way.
If I had one more thing, sorry. Let's go back to your point about communication. That's the other thing. And this is something that the Faculty of Science has embraced like no other that I'm aware of it, with regards to actually creating courses on how to communicate science. And that is making a huge difference. And it's all, I think it is mandatory for our RHD students, or we encourage them that they should all do communication in sciences, so they actually know how to talk non-science, as it would be, and to get the messages out there to make it really clear what we're trying to do. Because I think a lot of it is kind of lost in translation between an academic science speak and the general public. If we can actually get people to understand what our mission is about, I think that's a very important thing. And I really commend this faculty for all its innovation in that space. Has been remarkable.
And I totally agree with that. Now, science communicators are so important. So someone out there before said they were one. You're doing great. We need more.
Yeah.
I'm really sorry for those who didn't get to answer their questions, but we've run out of time. Incredibly.
Wow.
That has absolutely flown by. So just to wrap up, I'd like to thank again our panelists, Stacey, David and Shi. If we could give them a round of applause. I've had the pleasure of meeting panelists over the last couple of weeks, and it's been wonderful. So thank you sincerely. As I mentioned, if you are interested in engaging in this society and getting in the Bridgerton swirl here, I kind of, if you are a company and interested in working with us, Andrew Rudge is the Business Development Director to get in contact with. If you're an individual that's interested in helping a research team, mentoring a group, you've got some specific expertise you think would be helpful to our mission here, you're interested in startups or anything, Stephanie Adams is our head of community and communications within my group. So there's two people you can actually contact. So that's it. Thank you. I've been asked to remind you there's lots of other events the rest of the week, so please join in. And there's a whole series of events through the Faculty of Science. They are excellent. I'd encourage you to join as many as you can. So thank you very much.